All right. So today we're going to look at Ampere's law, which, following sort of our setup from last time, we started by integrating for electric fields and figured out that since charges generate electric flux, there was this nice relation with Gauss's law that allowed us to use symmetry to find E fields quite nicely without having to go through the full integral. Because we know that charges are generating flux because point charges are sources and sinks, so that was the relevant thing to use was flux. But we know that breaks down for magnetic fields because we know what Gauss's law says for magnetism. It says your net magnetic flux is zero through any closed surface. So instead, we're going to define a new concept. So this is a sort of cousin of flux. And like many people, I call it circulation. So charges certainly generate flux. It's flow in or out of a surface. But currents generate fields that loop around them. So we're going to call this concept circulation. It's the net amount that a field is sort of spinning or going along a certain path. So for our Calc 3ers in the audience, it's no coincidence that this E field looks like the textbook picture of divergence, and this one looks like a textbook picture of curl. So we'll see that that's a very important relationship. And it's actually how you can come up with some of these formulas is by leveraging some knowledge of divergence and curl. So Ampere's law looks very similar to Gauss, except we define this quantity, this path integral, as the circulation. So you're not adding up the amount of E that penetrates a surface, which is what Gauss's law says. But Ampere's law says add up the amount of field that's spinning around a path. So it's not a perpendicular, it's a parallel. So this quantity, I don't know if it really has an official name. I've called it circulation. And a lot of people also do. So I think we're going to call it circulation. Because that rolls off the tongue a lot better than the path integral of the parallel component of B dl. So just like in any situation, we can always use Ampere's law. This is always true that your circulation is going to depend on the net currents enclosed, which should make sense because if your field is spinning around a point, there must be something generating the spin. So this is our most common thing that we'll draw, this Amperian loop, is circles, because if you have nice, clean, single wire sources, we see that it's going to perfectly trace out a circle. So it circulates. And we're already should probably be making some connections. A 2 pi r with a B field? I know where I've seen that before. And it is actually true that there's a missing term from this Ampere's law that we won't talk about in APC. It turns out you can also get magnetic circulation around changing E fields. And you can think of that as like an analog to Faraday, because we said a changing B field induces an electric field. Well, there has to be some symmetry the other way. So it turns out if you change the electric flux through an area, you'll generate a circulating magnetic field. That's known as the Ampere-Maxwell law. We may talk about that at the end of the year just for fun, but this is what we'll be using. All right, so we have these currents that are just existing in some region of space. Of course, they're carrying current either out of the page or into the page. All right, determine the magnitude of the magnetic circulation along this dotted path shown. So, of course, we want the magnitude of it. We have to talk about orientation, like these paths do have an orientation. Take it to be counterclockwise in general if you want to be precise, but it really doesn't matter. So, Ampere's law says magnetic circulation is just equal to mu naught times I enclosed. So we want the magnitude of it. So just like if we wanted the net magnetic flux, net electric flux, we just sort of look at what is being enclosed. So what is being enclosed? Well, let's say out of the page is positive. We have a 1I going out, a 5I going out, and a 2I going in. So just make sure that we're subtracting those opposite currents. So we get a 1, a +1, a +5, and a -2. which gives us 4 mu naught I. And again, there's no issue here if you picked the other current to be positive, because you'd still get the same net current. We just want the magnitude of it anyway, or the absolute value, I should say. All right, so why can't we actually find the B field along this path? So why, like Ampere's law is always true, but why isn't it useful on this path? Well, just think about it. This is going to be an absolute mess because you'd be generating a B field that way at that point. This generates sort of 5 of those, so there's no symmetry. That's really just the quick answer, right? We can always calculate flux using Gauss's law, but only if there's symmetry can we find the field. So there's no symmetry. So I think we should write the classic statement. Ampere's law is always true, but not always useful. All right, now let's draw another loop that maximizes magnetic circulation in this problem. So magnetic circulation is proportional to the enclosed current, so I need to figure out how to maximize the enclosed current. So our issue here is that this loop enclosed some current that was fighting our two sources. So we want just any sort of loop that encloses just the two larger currents. So I'm going to pick that, right? Because this encloses the larger of the two current signs and none of the canceling ones. So we would say that the max value is, well, I'm enclosing an I, a 5I, and nothing that cancels, so it's just a 6 mu naught I. So here's how we apply it. This is going to look very similar to Gauss. So first, you got to have symmetry. So this problem, absolutely not. There's no symmetry. But a single wire, absolutely, circular. Inside a wire, circular. And there's only 2 possible Amperian loops that we'll really draw that are useful. Just like the integral side looks scary, like I know that's a very scary looking symbol, especially with a closed path. It's never hard. Just like Gauss's law, the integral always worked out because you could pull out the surface and make it EA. Well, Ampere's law, you can always make it BL. So for wires, those have circular symmetry, so we'll use a circle. So BL will be B times 2 pi r. And the other case we'll have is a rectangle that's sort of partially in and partially out of a distribution. These are more of your infinite slab type things. We'll see we get BL for that shape. So not a whole lot of variation. The difficulty comes from the right side, because how do you find the enclosed current? Well, counting, that's the easiest way. And then our density function, this goes way back to our first unit. We actually defined current density, because we have all different flavors of charge density. But the only type of current density we've used is J, which is defined as current per unit area. Because currents are sort of traveling through these cross-sectional areas. So it makes sense that there's only one type of this current density, because it has to be how we define current in the first place. Of course, there exist other types of densities if you look in higher level texts like Griffiths, but we're fine with just J. So if you have an enclosed area, you just multiply J, if it's uniform, by that enclosed area. And if it's not uniform, you have to do an integral. You integrate J dA. And area is a circle, so this is another one where we build our areas out of circular rings 2 pi r dr. Then you set your two sides of Ampere's law equal and solve. Because you have BL, it's going to be equal to mu naught times I enclosed. All right, this is the simplest case. We have done this many times. or at least use the results. So we kind of should have the power of hindsight to know what we want the answer to be. We want the current, or sorry, magnetic field generated from a long straight wire. All right, not the worst circle tool I've made. It's kind of distorted, but we'll make do. All right. So we want to calculate the magnetic field, a perpendicular distance r from this wire. So it's carrying current out of the page. So right-hand rule tells me that my thumb is the current direction, so counterclockwise. So this means at all points, we can draw ourselves some magnetic field that is wrapping around like this. So of course, this is telling me to draw a circle. It's telling me to draw a circle. So our Amperian loop is going to be a circle of radius r. And why? Well, what's the circulation? Well, again, circulation is defined. I'm going to drop the path symbol. It's the amount of distance the field is circulating parallel with the path. So it's tangent to this path or parallel to it at all points. So what that means is that we can just write this as B times L. And we can go one step further because we know how long it's been spinning around the path for. It goes the entire circumference, 2 pi r. And we'll verify that we get the expected result for a long straight wire. So what does Ampere say? Ampere says that magnetic circulation is equal to mu naught times the enclosed current. We said that our circulation was B, because that circulated for 2 pi r, so B times 2 pi r, and our enclosed current is just I. I just have to count it. Nothing weird there, right? It's just literally an I. So notice I just divide both sides by 2 pi r, and I get, unsurprisingly, mu naught I over 2 pi r. And of course, here's our daily brag, where we can say as expected. We do know this is definitely our B wire formula. All right, next case of the wire we have is inside a wire. So we're going to go inside and out. So instead of our wire just being a point source, we're going to think of it as having some thickness, capital R. So first, determine an expression for the magnetic field strength for outside the wire, justify our answer. Well, this is a determine, which means it's pretty easy. So we haven't encountered this in the past, so let's say that this I is going this way. So again, right-hand rule says I'm going to pop out of the page. It's going to pop out of the page up here and into the page down here. So outside the wire, well, what does it look like? Again, just like with Gauss's law, we have like our equivalent of the shell theorem. So it just looks like a wire. So what do we mean by that? Again, we can just say that if you're ever outside a current distribution with symmetry, you can always just use the outside formula. So B is just going to be mu naught I over 2 pi r, where r is this distance from the center. So just like with electric fields, whenever you're outside a distribution, you just do that center to center distance idea, where you take this distance is r. We have just been pretending our wires aren't thick at all. That doesn't really change anything, though. Still mu naught over 2 pi r. What is the current density inside the wire? So inside, well, J is defined as current divided by area, which is the total current divided by the total area. So what is the total current? Well, it gives it to us. The total current of the wire is I. What is the total cross-sectional area of the wire? So again, this is not the surface area like with Gauss. All the current is distributed in sort of this cross-sectional area. So we're looking at different segments there. So what's the cross-section that it's distributed through? Well, it's just a circle, and it has radius big R, because that's the wire's radius. And again, this is a constant number, right? This is because we have constant I and a constant big R. All right, now we can do Ampere to find our field strength inside. So Ampere's law says magnetic circulation is equal to mu naught times I. And once again, for the same idea as before, if we have this sort of rightward current, we know it's going to be spinning around in circles inside the wire. So it might help to actually like take a top view here. If we're looking at the sort of top view of the wire, if we're inside, you can imagine taking a little circular loop there because it's going to enclose sort of partially the current. It doesn't enclose the whole thing, and it just encloses part of it. But depending on which way you take the current, I actually had it coming at me. In this case, we can see it's still going to circulate sort of around like that. So once again, we draw a circle. B times 2 pi r is equal to mu naught times I enclosed. So now let's find I enclosed. And again, we'll show two methods for this. So first, I enclosed is just going to be equal to the constant current density J times the enclosed area. So we define J as the total current divided by the total area. And then what is the enclosed area? Well, if I look at my top view here, I'm enclosing a circle again, but it's not the big circle. It's a circle of radius little r. So we see the pi's cancel. So we get I times this quantity, little r divided by big R all squared. And this is very similar to the result for the insulating sphere with Gauss, because the insulating sphere with Gauss looked like Q enclosed is Q times the cubic ratio, which makes sense because that used volume, this uses areas. So I actually have a nice term for this. We call this the area fraction. So that avoids calculating current density entirely, because you know that the fraction of the squared radius you enclose is sort of the area fraction. Because if you go halfway out of the circle, you're not enclosing half the current, you're only enclosing a quarter. So that allows us to just plug and chug now, because we know that B times 2 pi r is equal to mu naught times I enclosed, which is this object. So we can cancel one of the r's and divide by 2 pi to get B is equal to mu naught I over pi big R squared times r to the 1. So once again, we see an analog to Gauss, because with our uniform current distribution, we have a linearly increasing V field. And again, that arises from a same idea, because our concept we're integrating over goes down a dimension, as with the thing we're integrating our density over. So it's that same relationship here that we get a linear out of it, because circulation increases linearly, but enclosed current increases quadratically. So you're left over with this extra r. All right, what does this look like? Well, it's that graph that we're hopefully pretty good with already from the Gauss's law part. I want the solid line, please. Thank you. But it's not totally the same. So this is proportional to r, but this is proportional to 1 over r, because B from a wire is 1 over r, E from a sphere is 1 over r squared. And we do know the maximum value of this. This is just when it looks like you're just right outside the wire. So that's mu naught I over 2 pi big R. So again, there's a reason I organized the course this way, so we can see all the similarities. And just like after doing the insulating sphere, we gave ourselves a density function. Now we have a density function in our wire. So let's figure out how we actually get current from a density function. So current density J is defined as the current passing through a cross-sectional area. So this means the total current is equal to all of the current per areas times their little area enclosed. So just like last time where we had this dv, q is the integral of rho dv, so we had to write v is 4/3 pi r cubed, we took a derivative. Same idea here, right? What is a? Well, this is a problem with circular symmetry. So the area of our enclosing shape is going to be a circle, pi r squared. So that means dA is equal to 2 pi r dr. Right? The extra area you get is equal to the ring, 2 pi r that you're at, times its tiny little thickness dr. So our total current is going to just be equal to, well, we're given a density function. It has radius big R. So I sweep out segments of wire with 0 radius, and I keep building extra rings until I get all the way out to the big radius. Our density function was CR, and dA is 2 pi r dr. So don't forget this. This is, of course, just like I said, it's a big mistake with Gauss. It's also a big mistake with Ampere, forgetting this little differential for your area. 2 pi and c are constants. So 2 pi and c can come out. We obtain an extra r, making this r squared. So we get 2 pi c divided by 3 times r cubed from 0 to r, which is, of course, just going to be 2 pi c big R cubed divided by 3. So this is our total current in the wire. So we might want to just make a note that this is I total. So once again, if you have I total, it's quite easy to find current outside because we just use our shell theorem, right? This looks like a wire when we're outside, right? If you're outside the wire, just the nature of the shell theorem in these fields, it hides all information of what's going on inside. It just looks like a wire to me on the outside. So I know it just looks like the B field from a wire. B is mu naught I over 2 pi r. And it's going to look complicated because we have this really complicated looking expression for I total. Like this is our expression for I total. 2/3 pi c big R cubed. But it's a constant, right? Because it's big R, not little r in here. And I actually would argue we might want to just leave it like this. Because this makes it really clear to the reader that this is a current carrying wire with a current given by this expression. You could simplify further, right? You get a pi that cancels out. Oh, we are going to have to check continuity later. So let's simplify it. Just because we're going to check continuity in this next part. Let's see. 2 and pi cancels from the numerator, and 3 goes to the denominator. So this is mu naught c capital R cubed divided by 3r. If I simplified wrong, we will find out in the next part, and I'll fix it. But yeah, I think cancel the 2 pi's, bring the 3 down, and I got a CR cubed. Yeah, I think that's right. All right, what's going on inside the wire? Well, same idea as last time. Because we have our wire that looks like this if I'm looking at it from the front. And we're going to draw ourselves a little cross section. And it's going to enclose some sort of a current that we're interested in. And of course, it's not the whole thing. It's not the whole thing this time. So we know that the integral of B parallel dl, which is that magnetic circulation, is equal to mu naught times I enclosed. It's circulating around a circle of radius r, so 2 pi r for a circumference term, and then we got to figure out I enclosed. Oh, I didn't say check for continuity. We will anyway, because we're built different. So what is I enclosed? I enclosed is the same idea as before. We're integrating JDA, except if we look at what we did last time, we integrated all the way out to big R because we wanted all of the enclosed current. We don't want all of the enclosed current this time. We just want it out to little r instead of big R. So we plug in our density function. dA is still 2 pi r dr, and we get an answer. So notice I can save myself some work. I already figured out what it is outside the wire. So all I'm doing is I'm replacing this big R with a little r. That was my only cosmetic change, right? All the integration is the same, all the physics is the same. So I just need 2 pi c little r cubed divided by 3. And that's just how it worked with Gauss last time as well. All right, now we do it. Oh, we don't want to go to the slab yet. All right, we're back. Okay. So B times 2 pi r is equal to mu naught times I enclosed, which is this object. And we get some canceling, right? We get 2 pi cancels, and one of the r's cancel. So that's going to make this B is equal to mu naught CR squared divided by 3. So again, we can make sure that this makes sense, right? This follows my my E field theorem for Gauss's law. I claimed that when the density function is proportional to a power of r, the field inside is 1 greater. So you have a linear current density, so you have a quadratic field inside. We can also check for continuity. So we can check that at big R, this is mu naught C big R squared over 3. That was our in function. We can also check our out function, where our out function looked like this, mu naught C R big R cubed over 3R. Which, what do you know, it's the same. So I probably did do this correct. Again, it's usually rare for me to make physics errors, but algebra errors are a dime a dozen around here. So as expected, it is continuous. So we're going to draw ourselves a concave up curve here. And I know we know what the actual max is, but I think it's more telling if, so this is proportional to r squared, this is proportional to 1 over r because it looks like a wire. We're going to say this is mu naught I total over 2 pi r. I think it looks more clear this way, that like that's why the maximum is what it is at this point, because it looks like a current carrying wire. You've enclosed maximum current, but haven't started to fall off yet. So once again, that theorem still applies for Ampere's law for the same reason it applies for Gauss. Inside, it looks like the field varies 1 higher than the density. Outside, it decays like the distribution you're looking at. So it's a wire. All right, now on to some non-circular Amperian loops. So this is going to look very similar to our Gauss's law version of this, where this time we have a conducting slab of thickness d, but it's infinite in the xy plane. So it's a very, very, very large sheet of current, and it's stacked on itself a distance d. So it's essentially a big sheet of a bunch of wires coming at you this way, and they're stacked up a distance d. So we are given that it has a uniform current density J. It's directed out of the plane of the page, so we see a side view here. It's centered at z equals 0. So if we think about what this is going to look like, Our first claim is that the magnetic field is going to point to the left on this distribution when z is positive, and it's going to point to the right when it's negative. So here's one way to see this. So this works whether you're outside the slab or inside this sort of argument. So what I'm going to do is let's think about actually drawing sort of the swirling magnetic fields from these different wire components. So if I try to draw some circles here, we know that the magnetic field circulates around these currents, and it's going to be counterclockwise for these. So if I draw my counterclockwise circulating currents on each of these, we should notice something. Notice that if I were to actually overlap some of these adjacent circles, and it's not going to let me do it, but if we look at these overlapping circles, if I paste these circles on top of each other, which I should do because these aren't finite wires, these are infinite. This is an infinite slab, so I'm chopping these up into infinitely thin wires. Notice on this overlap here, the vertical components of these adjacent swirls are going in opposite directions, so they cancel. But what's not canceling is the vertical. So notice that we're going to get an entirely leftward field for positive values of z. And by the same argument, if we were to draw ourselves circles down here, we see absolutely the same effect. It still circulates counterclockwise. And adjacent swirls still cancel. But this time, it is the rightward field component that stays the same. And also, we get a side effect of b being equal to 0 right on the midline, because that is the only spot where these horizontal swirls cancel each other. So that's my way of justifying it. I'll show you another way. Let's do like an outside the slab argument. So let's pick some, we'll draw some currents here. Maybe I can do a better job of actually making them the same size. So let's say we're out the slab, and this is just the top layer. Now, it doesn't matter, because we know the bottom layers are going to do a similar effect if we're outside it. Without losing any generality, let's just pick this point up here. Let's pick some point up here. So what do we know? Well, we know that if I were to pick this current source, for example, we know it's going to generate a field that is perpendicular to its tangent vector, and this one circulates counterclockwise. So counterclockwise around this wire will look like that. And now, because it's an infinite slab, I can always find a neighboring wire that's going to be the same distance. So this one, I'm going to pick like that. And if I look at the field this way, this one also has to orbit counterclockwise, which gives that. And what do we notice? Well, if we were to tip to tail addition these, I think I need to make this one a little longer to really tell. But if we were to tip to tail addition these, notice they have exactly the same but opposite vertical components, leaving a pure leftward B field. And this works with all of the points on the slab because I can keep pairing them up all the way down. So I can pair this one with the wire over here and so on. And the one directly above it just generates a pure left field anyway. So that's how I would justify that. And again, it just says using a diagram. So by symmetry, we see components are going to cancel. All right, outside the slab is uniform. So we're going to take a little bit of a different approach for this one. So I like with the plane, with Gauss's law, I like the argument that as you go higher up, you get a sort of bigger vision cone. So you sweep out a bigger area. And the rate at which you're sweeping out area is quadratic, and the rate that field decreases is quadratic, so you get constant for the E field. That's how we argued that. For this, we're going to use an argument that works for the plane as well, of charge, but it's a bit different. So this is kind of a bit hand-wavy. Like, Don't get me wrong, this is totally hand wavy. It can be hand wavy because we're going to prove it using Ampere's law. So we're going to prove it. So this is just trying to get some like just conceptual ideas to why. So we're going to say that the plane is infinite. Infinite, which means there is no way to distinguish any 2 points in space above the slab. So what do we mean by that? So what we mean by that is suppose I am some distance above the slab right here. What do I see? Infinite slab, right? So if I'm asking someone, I'm right next to my hand here. What do you see? I see hand in every direction. Well, it's infinite. So even if I'm a higher distance above the slab, I ask this person, what do you see? I just see slab everywhere. So this picture has to look the same no matter where you are in space because it's an infinite slab. So this means B must be the same everywhere outside. Because how would the slab know how far away you are from it? We have to, so again, this is definitely a very loose argument. And you can definitely use a similar idea as the vision cone. I just wanted to present this one because I thought it was kind of neat. So the skeleton of that one says try to sweep out how many wires you can see in your vision cone. So here, I might only see wires out to maybe this area of the plane. But if I go higher up, I might see wires all the way out here. So my distance is increasing linearly, and so is and the wire field decreases linearly, same idea. But I thought this was kind of interesting. Like there's no way to tell whether you're slightly above the plane or really far above the plane because all you see is plane. So there's no way the magnetic field knows either. Kind of odd, but of course it's odd. It's an infinite conducting plane. It's infinite. All right, Amperian loop. So what are we going to draw here? So let's do the inside the slab case first. So we know that B points to the left above the midpoint. So, and we also know it's 0 at this midline. So if I draw myself a loop maybe like this, because we don't want to circle anymore because it's not truly circulating because all the swirls are adding to the left. So if I draw myself this loop, it will work out because we see it's going to circulate along the top only. So this is the only spot where we're going to get circulation because I'm going perpendicular to the field in 2 of the directions. So that's not circulating. And there's no field at the bottom. So that's not circulating either. So we are picking a rectangle. So now we'll derive ourselves some net magnetic field directions or strengths here. So we'll do inside and outside. So I did have a typo I had to correct here because I had my wrong slab distance. So inside, well, this is a nice picture. Let's steal it. Let's steal it and move it down here. So we're a distance z above the midpoint. So let's call this distance z. Now, it's an infinite slab, so I can't use any physically meaningful distance on my other side, right? It goes all the way this way. So we're just going to call this x. And as with our Gaussian surfaces, if you make up some fictitious length that doesn't mean anything, it better cancel. So what does Ampere say? Ampere says that the magnetic circulation is mu naught times I enclosed. And my circulation is just going to be B times X, because the only place I get circulation is up here, because B, it points to the left up here, So no circulation here, and B is 0 at the midline, so there's no B field. And what is I enclosed? Well, we have a uniform current density J. So if we find the area we have enclosed, we can get our current. And that's pretty easy because we drew ourselves a rectangle. So what's the area of this rectangle? Well, this rectangle is just Z times X. So we see that, as expected, our magic mystery length X that doesn't mean anything cancels. So we get B is equal to mu naught times J times Z. This should make sense because as you move up from the midpoint, you're enclosing more current, so we should get more B field. And we know that in our problems with uniform current density, we expect a linearly increasing B field in the inside region. All right, drop my pen. All right, outside the slab. So this is going to be very similar to the argument we made using Gauss's law when we did this one for E field. This time we're just taking our loop and we're going outside the slab. It's not a good job of being rectangular. All right, so same idea as before. No field, no circulation. Perpendicular, no circulation. Perpendicular, no circulation. Parallel outside the slab, absolutely, we get circulation. So this distance is X, and then this entire distance is Z. So let's set up and see where we get a difference. So Ampere's law, no difference there, right? Mu naught I enclosed is the circulation. We still circulate for B times X. And I enclosed is still the current density times the enclosed area. And here's where it changes, because we are now outside the slab. And we need to make sure we're only multiplying by the enclosed area that is actively enclosing current. So there is no current up here. So we do not want this area involved. The only part of our slab with current in it in our loop is this area in purple right here. And what is that? Well, this is why it matters that we're outside, because this incorporates the slab thickness. So this distance right here is going to be D over 2, because the whole slab thickness we said was D, which was my first error. I made this 2D in a prior version, didn't fix it. So that means this area right here is going to be D divided by 2. So I'm not enclosing a variable length of my area. It's going to be a constant D over 2, because no matter how high I am above this slab, I'm not enclosing more current than I was before. So D over 2 is my dimension one way, and X is the other way. So the X, of course, cancels. So we get B is mu naught JD over 2, which is a constant. As expected, we get a uniform field anywhere outside the slab. We can see continuity also works because if Z is D over 2, they match. So we can imagine what this looks like on the graph. It's the same as the volumetric density. Okay. Sketch B is a function of Z. Label any known intercept extrema. Well, we said is a linear increase inside, and then it is constant. So what is this? So this is linear. This is proportional to Z. And this is a constant value, mu naught JD over 2. And we know it's continuous because if Z is D over 2, the fields match. Because mu naught JZ would equal mu naught JD over 2. All right, suppose we gave our slab some current density that varied. Describe how it changes in each region. So, outside is no change, because we are given that this current density is the same on average. It just increases from the center. So, as per usual, we said by nature of all these shell theorem related corollaries, you have no idea what's going on inside if you're outside, so you can't tell. But what's happening inside? Well, we use our theorem, right? Our theorem says that the field, electric or magnetic, increases via one more than the power on the density function. So inside, B is going to be proportional to Z squared. So it's going to be concave up. So this would be a quadratic increase up to the same maximum value and then level out. All right, we have one more thing to do. Just like we talked about the capacitor, which was a way to trap electric fields and create a uniform electric field, our method of creating a uniform magnetic field is known as a solenoid. And this is really a slinky shape. So we know how to find B from one loop. So if we just loop, 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 loop all the way around, we know that the magnetic field from a loop points directly along its central axis. So if we just keep looping these objects together, we have created one long uniform B field down this axis. So that's how we confine or trap a B field and make a uniform B field, is by tightly winding a bunch of coils. So to define the magnetic field from a solenoid, of course, we pretend edge effects don't exist. Our solenoids are very long. So the best way to get a good solenoid is to have a long solenoid with many, many turns. So we'll talk about the turns per unit length. So it's how many coils you have per meter. So we say the field is uniform inside and 0 outside. And you might get some edge effects if you don't have a lot of turns per unit length. So if you do, this value is called lowercase n, the turns per unit length. That's how we confine or trap these B fields. So let's do it. We're going to calculate the magnetic field inside a solenoid of length L. The solenoid contains capital N turns of wire carrying a current I. So first of all, why does drawing an Amperian loop strictly inside the solenoid not help us? So we do know that the field inside the solenoid does... Let's use my straight line tool. How about that? We do know the magnetic field inside the solenoid. Actually, I had to test my right hand drill there. We do know that the magnetic field inside the solenoid is uniform and points this way. So why don't we just want to draw something like this? Why don't we draw this rectangle? Well, of course, if we think about it, why this rectangle doesn't help is because we know that the magnetic circulation is equal to mu naught times I enclosed. So if you're fully inside, I enclosed is equal to 0. So if you're fully inside, I enclosed is equal to 0, which is not helpful at all. So that's not helpful. Because we want some non-zero value so we can solve for B. So we want to actually draw this Amperian loop that goes somewhat in and somewhat out. So we're going to draw ourselves this loop, because you have to have a loop that encloses current. So for the same reason, this loop is also not a good choice, because it still encloses no current. So we want something like this. I like to center it on the midline, and of course we can come up with some values here. So we're going to say that this length, this is the only relevant length, is x. And since this field is directed along the axis, just like in the case of the slab, these pieces do nothing. And since B is 0 outside, because we're neglecting edge effects from the solenoid, there is only one contribution to our circulation, and it is this portion. So we're going to pick a rectangle partially in / out of the solenoid. And this is nice because this turns our circulation into b times x, because the other three sides are 0. Because our vertical traveling pieces, so if we actually draw ourselves the way we've been moving around this, our vertical traveling pieces, it's perpendicular to B, so it's 0. And outside the solenoid, there's no B field, so it can't circulate if there's no B field. So the only contributor is this side on the bottom. What is the turn density N, defined as the number of coils per unit length? Well, we just do the definition. N is turns per unit length, which can be thought of as total coils divided by total length. And if we look at the problem, it was given to us that we have N total coils, and it is a total length of L. So its coil density would be capital N over L. So this is just like any other density, right? It's a number of things per other thing. So charge per meter, current per area. So this is coils per length. All right, now let's do it. Let's find the magnetic field strength inside. So Ampere says magnetic circulation is mu naught times I enclosed. We said our circulation only occurred a distance x along our loop. And now we got to find whatever I enclosed is. So just like before, we can always find the enclosed current by multiplying by some sort of a density. So our enclosed current, it's not going to be all the coils, right? You technically could, because of some of our assumptions we make in this class. You could enclose the whole thing. You make your loop length L, and you enclose all the currents. It'll get the same result. But for my enclosed current, I know it's going to be I times enclosed coils, right? Because I need to figure out how many coils my loop is enclosing. Because this is clearly not all of the coils, so it's not capital N. So I need to figure out how many of these currents are being trapped in the loop. Well, that's why I had us define the density. Because the enclosed coils is just going to be the coils per length times length. And we do have an expression for that, because coils per length was defined as capital N, little n. And what is the length enclosed? Well, the length enclosed is x. And we did go a step further. We did define what that is. We said lowercase n could be written as capital N divided by L. And that works as well. So now we can get our B field, because we can just say that B times X is equal to mu naught I times N over L times X. So this means B is equal to mu naught times N over L times I. So we'll move some things up here to give some more space. So this is the B field inside a solenoid. So notice it only depends on 2 parameters. Technically 3, but really 2. So I like to write it like this. This is not how the AP formula sheet writes it. I write it as mu naught times the quantity, capital N divided by L, times I. And again, that is actually lowercase. This is lowercase n, so you'll see it written in the formula chart as mu naught lowercase n times I. I like to just recognize that it is the density that matters, not the coil number, right? Because if I have a lot of coils that are spread all the way out, that's probably not going to be as strong as the same number of coils that are tightly wound. So what do we notice about the field inside a solenoid? Well, we said B equals 0 outside, and B equals mu naught n over L times I inside, and that's going to be uniform. So those are our cases of Ampere's law to know. So we need to be able to mess with wires, maybe a slab or two, and definitely the solenoid one. So the solenoid one has this very non-obvious at first glance Amperian loop to draw, that you want this sort of half in, half out idea to make sure you're enclosing some of the current loops. So this is going to look very similar to like our capacitor field. So that's why this is studied, because if we look at B versus R for a solenoid, is a constant field inside, and then we assume it drops to 0 outside. So of course, we can see like some clearly non-physical behavior happening here, like at the boundary of the solenoid, which is why edge effects really exist, but we always pretend they don't. So that's Ampere's law. Got through that a lot quicker than Gauss. It's a lot easier after we've been introduced to these things before.